Thank you. Thank you to the organizers for having invited me. It's giving me the pleasure to visit the main breeding areas and to continue talking about food and feed. After the brief presentation made of me, so I'm Francis Enjalbert. I spent my academic career that I finished 15 months ago as a teacher. I was a professor of animal feed in the Toulouse National Veterinary School, and I was focusing on ruminants and more specifically dairy cows. So today I'm going to talk about what we are calling currently the metabolic stress in dairy cows. This notion of metabolic stress corresponding essentially to a deficit or an imbalance in diet due to the start in lactation, but not only, and to which a dairy cow has to face. It has to adapt, and we'll talk about these reactions, not deeply because we won't have time, but broadly. So we'll talk about the adaptation reactions, and as any of these, they can be either very positive and lead to a correction of imbalances or have collateral effects can be highly detrimental, leading to zootechnical or health disorders that can be observed during peripartum for dairy cows. This metabolic stress has several key elements. One of these is the rapid increase in dietary needs before calving. You have references here, one being the middle of the drying period, and here you have a graph of what the dietary needs are for dairy cows, and for our American colleagues it is very small, but an average dairy cow producing 40 liters of milk. But in a few weeks, fortnight after calving, you can see quite large increases. The energy needs are being multiplied by at least 2.5, and the needs in proteins and minerals, I'm mentioning here just calcium, are nearly multiplied by a factor of 3. So you have skyrocketing in needs, and it corresponds to a request of the udder. And this should be normally offset by an increase in ingestion, but we know that ingestion is not corresponding to the need, thus a metabolic stress with nutritional acute stresses. So there are two aspects trying to face these, the breeder and the cows. The cows is increasing its ingestion, and the breeder is, or the grower is changing the diet. So you can see an evolution of the diet. You have a classic example here. You have a diet with silage, some straw for dried cows, cereals, and meals, something classical. And you can see the drying period just 2 weeks before, or after, sorry, you have an increase in ingested quantities. This is the decision of the cow, but you have also a change in the diet compositions. Beyond these, since the ingested quantity increases, we have where the quantity of each ingested element increases as well, and its proportion is in the ingested quantities. If we look at what the cow is eating between drying and the second week, classically speaking, there is a multiplication of by a factor of 2 of starch. Fibers decreases as a percentage of diet, but not in quantity, and there is a sensible increase in proteins ingested. The problem here is for animals is the more or less rapid increase in ingested starch, and you can see here the known effects. When we have an increase in starch ingestion, classically speaking, we also have an increase in the production and concentration of volatile fatty acids. And these SCFAs by osmotic pressure will modify the ruminal epithelium. In extreme cases, it can go up to a rumen ulceration and lead to a decrease in pH. This will of course, led to the creation of histamine, more in this case, and the release by microbial populations of lipopolysaccharides that are constituents of bacterial cells. And with damage to epithelium, these molecules that are not or little absorbed will be absorbed beyond these phenomenon, and we have been looking at these aspects for some years only now, it's very recent. Part of the starch is not digested in the rumen and will go in the hindgut and will go to the large intestine, and here we can have starch fermentation leading to acidosis, which is called intestinal acidosis. And here again, there is a production of lipopolysaccharides that are more easily absorbed by the mucus of the large intestine rather than that of the rumen, as it is a multi-layer one, not permeable, whereas the mucus of the large intestine is very thin. Thus, with other phenomena being added, but I told you that I wouldn't go into the details, we have an absorption of LPSs in the large intestines going into the portal circulation, reaching the liver, and everything in the digestive tract comes from the liver, and the liver is the first filter to stop those molecules that should not be disseminated in the whole body. These molecules will lead to a liver inflammation with a production of acute phase protein. Then it'll go into the peripheral circulation of some liposaccharides, a majority having been detoxified. And we also have cytokines, mediators of inflammations for some of them. This will lead to a systemic inflammation, I mean here, of the whole animal organisms. So, in this notion of metabolic stress, the animal, because of its increased ingestion in starch, the animal will have to face inflammations. Second point, energy deficit. Around calving, appetite involves slowly, in comparison to energy needs, with a decrease, or a sharp decrease in appetite the week before calving. And during that week, most of the dairy cows start having an energy deficit. This deficit is something physiological. You can't say that cows cannot face these. They can, and we'll see the mechanisms on the next slide. But we can consider that a certain level of physiological reserve mobilization in animals. This level is being mobilized or modeled in the INRA opus with different variation curves of these reserves expressed in UFs. And of course, all curves cannot be seen here, unfortunately, but it depends on the dairy production. The higher the production, the higher the possibility of the animals to mobilize reserves. This reserve mobilization is being directed by the hormones, and the director here is the growth hormones. It favors and direct the nutriments towards the udder. A dairy cow has a high production. If we simplify, it means that this level of growth hormone secretions will direct the nutriments towards the udder and favor high production levels. Among those nutriments that go to the udder, we do have glucose. Dotted arrows are results, and this growth hormones will direct the nutriments towards the udder, among which glucose, hence a decrease in glucose blood concentration. This decrease will itself lead to a decrease in insulin secretion, as we see for all animals, whether ruminants or monogastric. This defect in insulin will block one of the normal actions of the growth hormones. One of these normal actions is to allow the insulin growth factor secretion, and this liver secretion of insulin because of HGH must be stimulated by insulin. So at the beginning of lactation, you have little insulin and very little IGF. This insulin and this IGF normally are those hormones conditioning the deposit of energy in the adipose tissue. The ones created, the cows, has made a good job. Logically, the cow knows that it is to face periods of energy deficit, and from an hormone standpoint, it is ready to avoid any deposit and favor the mobilization of energy reserves. To make sure it works efficiently, it is a lot of protections. There's little insulin, but the adipose tissue resists this insulin. Under such conditions, the other actions of the growth hormone will become dominating, and this action will increase the sensitivity of the tissue to catecholamine, mobilization hormones. Thus, you have a high mobilization of the reserves from the adipose tissue. Normally, this hormonal orchestration with the growth hormone as the director gives priority to the other modality, being to favor the use of reserves and essentially the use of adipose reserves. This use is on triglycerides in adipose cells being hydrolyzed in the adipose tissue, and will mean that two molecules will go into the blood. Glycerol, I'm not mentioning it here, but glycerol is a precursor of the synthesis that can be turned into glucoses. It can slow down the slack in glucoses, but there will be a mobilization of of non-esterified fatty acids, NEFA. They increase the resistance of the adipose tissue to insulin. These NEFAs will be disseminated into the body. Small part is being taken up by the udder for the synthesis of the milk fatty material, but most is fixed by the liver. And this liver may have two possible actions on the NEFAs. The first, it burns them to create energy, in the ATP meaning of the word, acetyl coenzyme A being the key here, and the other action is to re-esterify them into triglyceride. They'll be exported into the blood and thus will give fatty acids to other tissues and supply fatty acids to the udder. This is when everything is okay. But when there is a high mobilization of the adipose tissue, remodeling phenomenon of this adipose tissue exist, and these phenomena will lead to the release by this adipose tissue of cytokines. We have already met them. Okay, they have been secreted by the liver when there was a lipopolysaccharide, but they are secreted by the adipose tissue as well, and all cytokines are not pro-inflammatory, of course. The ones are here, but they will lead some typical reactions in the liver of inflammation. There will be modifications in protein synthesis, and these proteins are called APP, acute phase proteins. There's quite a number of them. A typical example is actoglobin, the one that has been mostly studied. Another one is CRP. If you look at the early medical analysis, you will be mentioned. It is quite classical for all species, and on all these positive protein of the acute phase of inflammation, there is an increase in secretions, and conversely, there is a decrease in negative protein during the acute phase, such as albumin. In other words, activity modifications connected once again to this inflammatory phenomena. This distribution of NEFA has been associated from an epidemiological standpoint to many disorders. When I'm saying associated, it means here that what we can see in experimental stations or in farms are a phenomenon or phenomena happening at the same time, or cause and effect results. Now, with all this data showing a relationship between NEFAs and other phenomenon, we have zootechnical phenomena, essentially a production modification. NEFAs, as I said, the energy deficit can start before calving, as appetite is very low the week before calving, and we can already have the beginning of lipomobilization before calving, and the biochemical marker being this presence of NEFA in prepartum blood. We can also have NEFAs in blood postpartum, and surveys do indicate that when cows have contents that are considered as abnormal pre or postpartum, this is associated to a decrease in milk production by several hundreds of kilograms. But recent data, you can see that even when retired, I still read a lot of documents, but recent data indicate that it's not that simple. And this graph here does indicate that depending on the quantity ingested 3 weeks postpartum, the gap between the real milk by cows and the milk that they should theoretically produce according to a standard lactation curve model, and depend on the concentration of NEFAs. We look just at the blue here, that is the abnormally high concentration in NEFAs. We can have cows that do have high NEFA concentration and a very good milk production if they eat a lot. Conversely, for those cows that do not eat a lot and have high NEFAs, it means cows that do lose weight because they'll stay. We need to know why they don't want to eat. Such cows will have relatively low productions. In other words, this overall measurement of NEFAs does not indicate everything. We can have cows that do accept thinning or loss of weight and do produce a lot of milk. So it is a question of management, individual levels of this energy deficit. There's also an impact on the production performance, and some surveys do indicate that when blood concentration in NEFAs are high pre or after calving, here you have a percentage of cows depending of time, a lower percentage for so concentration that in NEFAs are very high if we compare two types of cows. After the absorption of polysaccharides and after the release of cytokines by the adipose tissue, you will see an inflammatory reaction. I'm not going to comment upon all this slide because the organizers will tell me I'm speaking too long, but it's a very nice thing published by Bradford, NEFAs at the cell level, and because of a reaction chain I will not talk about, will lead to cell consequences depending on the impacted cells. But for liver cells, hepatocytes, we can see an increase in the secretion and formation of acute phase protein, APPs, and we can also have actions with the creation of cytokines, and this at the level of neutrophils. We'll talk about these in a few moments. These high concentrations were associated to a decrease in immune defense, impaired chemotaxis of leukocytes, those white cells that do ensure the majority of immune defense in blood, and chemotaxis is this phenomenon by which the cells will be directed to the area where they're is an immune defense to start. It is the kind of sat-nav of leukocytes. If it is not working, then the leukocytes will not concentrate on those areas. They will have to work, hence a decrease in immune reaction. We can also see a decrease in the production of immunoglobulins by lymphocytes. And as you can see here, the first part is something very much known. For fat cows, we have postpartum NEFA concentrations that are higher than for other types of cows. And at the same time, for those very fat cows, we can see immunoglobulin concentrations that are very smaller, hence a decrease in immune defense. And it means also a decrease in neutrophils activities, and these is one category of cells that is in charge of phagocytosis. They are to swallow a microorganism to destroy a pathogen. And this destruction in the biochemical intermediary requires the creation of myeloperoxidases, and it decreases when the blood concentration in nephers increases. And another marker of this energy deficit is the BHBA, and it is associated to such phagocytosis. The neutrophils do swallow pathogens before destroying them, and this phagocytosis decreases when the energy deficit markers increase. So besides all these actions, not direct actions of nephers, as I said earlier on, associations between the presence of nephers and abnormalities that are not cause and effect associations. There could be another effect when the quantity of nepher reaching the liver is very high, then this liver can no longer manage everything using the normal biochemical possibilities. It cannot burn everything, and oxidation intermediaries, the ketone botines, the BABH of the previous design, and the liver cannot re-export all the triglyceride created. Thus, there is an accumulation of lipids in the liver, and we call it a fatty liver. And these accumulation of lipids in the liver is called steatosis. It is the incapacity of the animal to completely re-export the triglycerides. This lipotropy mechanism, as we call it, is something very complex, because in order to re-export triglycerides, the liver has to integrate it into complex structures, the VLDL. If you look at your analysis bulletin, you won't find the VLDL, you will find the HDL and LDLs. Those are similar structures. And these VLDLs are a complex assembly of lipid compounds, free cholesterol, cholesterol esters, triglycerides, phospholipids, associated to a protein that is called ApoB protein. This complex assembly requires precursors. Some of these are not of a problem, whether it is cholesterol, as can be synthesized by the liver with ACE-CoA, if it is decreasing with peripartum, triglycerides, because these are the ones that want to move away. But one of the constituents of phospholipids that can be problematic is choline. It is interacting metabolically with methionine, which is itself one of the main components of this ApoB protein. So here we're talking about precursors and precursors issues. When we do have a steatosis, there's a decrease in hepatic function or liver function. Some measures were carried out on that topic for quite some time. We can see a decrease in two of the main functions of the liver, the urea synthesis to eliminate nitrogen excesses or nitrogen that cannot be used by the animals, and also a decrease in neoglucogenesis. And on this experimental diagram, when we induce a steatosis under experimental conditions, we do have an increase after the induction period of the concentration in liver triglycerides. It is followed by a decrease in the liver capacity to create glucose from propionate, which is the main precursor of this neoglucogenesis process. So the liver in this is the key organ. We met it when we talked about systemic inflammations for the absorption of polyliposaccharides, for cytokines released by the adipose tissue, for the metabolization of nephers, for the collateral effects when it cannot metabolize everything, that is the steatosis level. And some surveys also showed the liver function and some disorders that can be met on a farm. Here you have experimental results for liver function indices for cows having disorders in liver function create less albumin and more of this positive protein of the acute phase, and is associated to some health disorders. That is a low liver functions. That's for those cows that have the highest number of health issues after calving. The other item here is that low appetite cows, fat cows, do not eat a lot, have a negative energy balance, and there's a release of NEFA and BHB, liver damage. There's a systemic inflammation and a reduced immune response. And this is being added to the systemic inflammation effects linked to acidity. Another element is the oxidative stress. I want to redefine it. We talk about oxidizing stress when there is an imbalance between oxidizing molecules that are called the active oxygen derivatives, the ROS or ROM, if we add metabolite instead of species. And this is the result of an imbalance between the production of these highly oxidative molecules and the antioxidant defenses of the bodies. And this oxidative stress will lead to an aggression of the cells.
Without going into details, we have the free radicals and peroxides, and the antioxidant defenses are very well represented in our bodies. But there are a few which are dependent on nutrients. Now, for those nutrients which are particularly important, we have different vitamins. We have the C and the E vitamin. Well, vitamin C is not a problem. I mean, it's being synthesized at liver level. They are not so much dependent in normal conditions, of course. And then we also have the beta-carotene, which is an antioxidant. And then you have enzymes which are dependent on trace elements like the GSH, which is glutathione peroxidase, which is dependent on copper, zinc, iron, and manganese. There are some interactions between those antioxidating systems. A molecule just delivers hydrogen. It has to be regenerated, and it is being regenerated. Vitamin E is being regenerated by vitamin C, etc., etc. Those oxidating substances, those radicals, are produced by different elements within the organism. First of all, we have the mitochondrial respiratory chain, which is this is where the cell uses a normal way to function, and then in case of an unbalance, there is going to be an explosion of oxidants in the phagocytes. Now, for a pregnant cow, you will have this result here. It is being measured according to a particular method. You have an increase, a physiological increase, which is linked to the increase of metabolic activity of the body. The radicals also are being produced by macrophages and neutrophils as elements to destroy pathogens. They destroy pathogens really like a flame burner with oxygen. But then, of course, if you have to be very careful when you play around with fire, you will have problems to survive. Then you have the beta oxidation of fatty acids. They are being transformed in coenzymes, acetyl coenzymes. They also increase whenever you have a diet which is containing a lot of cereals. Here we have the molecule for oxidation that increases whenever the blood concentration increases in lipopolysaccharides. You observe this glutathione peroxidase, which is an antioxidant, and this here data indicates that there is a diminution of antioxidant molecules and an increase of substances that result from this oxidation process. So you have a certain oxidating stress that exists and which has several consequences. First of all, they are mediators of inflammation. This is the Bradford scheme that I showed you before. That show that those ROSs with the non-esterides fatty acids, the NEFAs, are going to interact, and this may alter the scheme of the different cells because of an DNA change, because of the components of the cell membranes, which are going to generate the exchange between the cell and the outside. So you have quite a number of different alterations, and those oxygenized radicals have two completely different phases. If you take the neutrophils or the macrophages, it will generate what we call phagocytosis. They will destroy pathogens, but on the other hand, it may also, if there is not enough antioxidating defense, it may damage the cells. And if you damage the cells that will defend the organisms in case of attack, it will imply this oxidating stress will increase the energetic metabolism and also produce a systemic inflammation and a reduced immune response. Changes in peripartum food intake and requirements. This is a kind of reminder of what I showed you before as concerns food intake. You see that the increase of ingestion will be lowered because of the ingestion or the production of fat. You see that calcium will bring along a reduction of calcemia, which is going to induce, because of the parathyroid gland, the production of parathormone, parathormone, which will rebalance and re-establish the calcemia. I would like to go back to this here, to the energetic homeostasis. We have a big difference between the energetic homeostasis and the calcic homeostasis. I told you before that the starting point of this creation of adipose tissues is a loss and a reduction of glucoses. And you see that, well, glucoses is being re-established, but not so much. It is extremely limited. The organism will react to a lack of glucoses by an increase of lipids. So it's not going to correct. It's going to last for quite a while. But as regards calcium, the reaction is perfect. Here we see that a lack of calcium is going to trigger off the creation of calcium. It is okay, but there is one defect, because it takes 1, 2, 3 days to set up and will not regulate for a few days. Again, a certain number of experiences show that the reduction, even of a low calcemia will, well, it's not the same as the clinical hypocalcemia, but subclinical ones will bring along a reduction of appetite, going along with the increase of energy deficit markers, and will also impair the immune defense because of this explosion of oxidative stress that help to burn down the pathogen. So we have a new item, hypocalcemia, as a factor of appetite reduction and reduction of immune response. Now, a big scientific debate is going on, but I know that you're not particularly worried. I'm not going to sort that out right now. But what is the starting point? The classical way of doing things is to look at the low appetite, fat cow, and negative energy balance, all this put together, going along with all the different elements that we just came across, and I'm not going to go back on details, but going along with NIFA and fatty liver, etc., means that the associations between NIFAs, reproduction problems, etc., are associations which are not highlighting causes and consequences. And recent data indicate that another source of energy deficit, in particular glucose deficit, putting almost everything in the same basket. I mean, it's not systematically the same, but anyway, another source of glucose deficit will reactivate the immune system, but it will, with intravenous injections of lipopolysaccharides. When you inject intravenously, the animal will identify as a microbial invasion and will start an immune response. And between the control group and the injected group, you have a glucose deficit at the beginning of lactation, which is going to move from 461 grams to 1,259 grams within a few hours. It means 2 kilograms of glucose per day. That's enormous. I mean, that's the lactose amount that you find in 40 kilograms of milk. So the priority of a milk cow, of a dairy cow, is to produce milk, but it's also to survive and to start setting on the immune system whenever it's necessary. So there is another origin that is the simple lack of energetic deficiency. And in this wonderful article of Horst, 2021, I can only recommend that you read that article. There are some details on this reaction, and the different elements that contribute to this immune system. First of all, the expulsion of the placenta, because it is recognized as a foreign body. So it is really how to eliminate something that does not fit into the body. So it will lead to the expulsion of placenta. The coming in of pathogens at the time of calving, which is normal. I mean, the uterus is open, the everything is mixing up, etc. So we have a lot of other infections. Then there is higher ingestions of starch that will bring about the incoming of lipopolysaccharides, which are going to start or to lead to an onset of the immune defenses, and then everything everything tends to indicate that everything that I've been saying before is wrong, but it's not completely true, and I do not want to quarrel about that. But what we see, thanks to those arrows, with all those arrows, that those relationships are quite numerous. And what is important for me is that somewhere a kind of vicious circle starts. And we always end up with the lipomobilization, modification, and this article does not say that it is a diminution, but it is a modification of the balance between immune system and inflammatory processes. So there is a reduction or an adaptation of the immune response and may lead to two big consequences. The first one is the sanitary problems that we call specific problems like acidosis, steatosis, milk fever, that may be clinical or subclinical, hypocalcemia, subclinical hypocalcemia, and it may also lead to more general problems, less specific, like drop of reproduction, of production, higher sensitivity to infections. And this is how we come up with metabolic stresses, where we have a certain number of factors which are going to lead to a whole bunch of reactions, having collateral effects, which are going to be quite numerous. And this will lead to my conclusion. The transition period for dairy cows is a real challenge in terms of digestive adaptation, metabolical adaptation, but it's also a challenge because it is a time where the immune system is really major, be it to keep up with physiological functions like rejection of placenta or to face microbial attacks, which are quite numerous at that time. So we have the going along with the risk of setting up a vicious circle with energetic unbalances that bring along a drop in the defense mechanisms, or even a disease that starts because of the presence of pathogens. Well, you see vicious circles that set up. So it is best not to get into this vicious circle and to have cows which are going to be correctly fed if we do not want to have those zootechnical problems. I thank you very much for your attention. And if I understood it right, there is no question right now. We will take those questions later.